Good afternoon, one and all present for the national level webinar on Silicon to Smart Home conducted by Mr. Balabharathi Mahalingam. I would like to invite the chief guest first and foremost for providing a part of his time to come and be a part of this event. I welcome you, sir, for the event. Next, I would like to welcome the students and participants who have gathered here to get a part of the event to understand and grasp the knowledge about the topic so that they can use it for further events and future programs. Thank you for being a part of this program and I welcome you all. I would like to invite Ms. Midha from 2nd MSc CS to provide a guest introduction. On to you, Midha.
Good afternoon, everyone, and a warm welcome to all of you. I feel extremely honored to introduce our chief guest, Mr. Balabharathi Mahalingam, who is working as Senior Physical Design Engineer at Moslogi Technologies, Bengaluru. He is well experienced in Synopsys to implement RTL to GDS2. He has 5.8 years of experience as Physical Design Engineer. He worked on block level PNR flow netlist to GDS2 implemented in advanced technologies, and also worked on static timing analysis in identifying optimal solution to meet setup slack and hold slack through clock tree optimization. He expertise in project management and reproducing quality outputs by prioritizing tasks individually. His highest education in Master of Engineering in Applied Electronics from Wellar College of Engineering and Technology. We are very grateful to Mr. Balabharathi Mahalingam for accepting our invitation and making his presence here. Thank you.
Continuing with the event, I would like to invite Mr. Balabharathi Mahalingam for his keynote presentation and his thoughts on the topic for the event. On to you, sir. The screen is yours.
Yeah, hi. Today I'm going to share a knowledge about silicon to smart home topic, how a semiconductor industry is working behind our all the daily lives. So it's just a glimpse of knowledge. How we are used to smart gadgets nowadays. We used to call every gadget as a smart, like smart home, smart TV, smartphones. Earlier it was just a phone, but now it is a smartphone. So it's all a tech development. So how an industry is revolutionary. So revolution like this from a normal cellular phone to a smartphone by combining hardware and definitely a smart software. Engineers are behind all to get it done, and finally it is provided to a customer and like our people. So here I'm just wants to share a few knowledge how back-end designings are going on for production of any chips. For example, nowadays for buying any mobile phones, everyone used to see processors, right? So Snapdragon 865, Snapdragon 555. So it's like different names. For example, for Qualcomm chipset, in case it is for a Samsung, we used to say Exynos chipsets. And in case for Intel, for laptop, we used to see AMD processors, Intel processors. So those are the chipsets. So how they are backend, they are actually doing these things. So that is what today we are going to see. So everything is based is the silicon. So that's what I just give my topic as a silicon to smart home. So let me share my screen. Moving on to the presentation first. So what I try to cover here in this webinar is like this is the abstract of my today's webinar. So semiconductor industry is the biggest industry in this world now. So it has the biggest revenue, like billions of dollars they are invested in just for R&D purpose. So it is to meet a purpose for something, for some need. So that is what every people and everything. If you see any industrialist like Tesla and those companies, Intel and those things they are industrialized people. They just wants to do a many research and development to give user end. Who are the user end? We are the user end. So we have to enjoy the benefit of the product. So they are keep on giving a R&D and they are trying to deliver new products, and that products we are going to enjoy the products. For example, we have a smartphone with advanced tech, we have smart laptops. So those things and all, how it is first planned and how it is researched and how it finally given to a development and it is going to user it. So that's what here. So here mainly topic I just covering here is so daily life with a semiconductor, and so just a glimpse of basic knowledge what is semiconductor and which is a game changer. So basically silicon is a metal, so that is the main thing. So where we are now revolutionized most in semiconductor industries because of this particular atom metal. Then how then ASIC industry and its role. So ASIC, it is application specified IC integrated chip. So one chip is specific for one particular purpose only. For example, if you take a bulb, smart bulb. So smart bulb is one of the ASIC. It is only meant to control the bulb activities only. So application specific, which application we are using, that is the specific thing we are calling it as ASIC. So what I am doing here in physical design engineering, that's what. So just you people just to know what is physical design engineering, how the people as a physical design engineering, how the people are working in a normal environment. So that thing is there, and also. Yeah, anyhow, so not only hardware, so so based on this band gap energy, so we will used to say from the valence band and the conduction band. So conduction band is the on the level where the particular element or a particular metal will conduct an electricity. So if you see insulator, the band gap between a valence band and the conduction band is very high. So insulator won't conduct an electricity. So that's what our wood, glass, and all won't even conduct an electricity. So you won't get a shock from the wood. So next to the conductor, yeah, it is a normal metal, any iron metal or any copper wire. Those are heavily conducting material. So you can get current easily pass through those material. Even water is a highly conducting. So that's what electricity easily passing through the water. So next coming to the semiconductor. So semiconductor name itself, it is saying it is partially conducting. When it will conduct, once if you give external potential. So that because of that external potential, it conducts an electricity. So that's what we used to call as the semiconductor. So whenever I want to conduct electricity, that time only I want to conduct. Not always. If an electricity is come, definitely it should not conduct. Whenever I need to conduct electricity, so at the time. So that is flexible for our semiconductor. So usually semiconductors have a 4 valence electron. So valence electron is an main thing. If you see on next slide, I can show you. So what is the valence electron? So if you see here, so actually this is a silicon metal. This is our silicon atom. So I just want to show this is the atomic structure of the silicon atom. Where you are seeing totally. So this is atomic weight and the atomic number of the silicon system 14. How we are saying is that 14 because there is a 14 electrons and 14 protons are there in this metal. So out of this 14, if you see, these are the 2 electrons and 8 electrons are bonded. So the remaining 4 electrons are outside the this orbit. So this is the main valence. This we are calling this valence electron because this is the electron which is used to conduct. This is the base. So these electrons will move away from this atom to other atom, which cause the free electrons to move forward. So that is when the free electrons are move forward. So that is the main reason electricity is connected from one area to another area. So that is the main reason. So that is what I am saying. So why I am saying when the temperature is high or when the temperature is low temperature, silicon is normally won't contact. So when the silicon is doped with some other phosphorus or boron, something if you are doping with that. So then only silicon is ready to as a conducting device. Until that is act as a normal intrinsic semiconductor only. So here the germanium silicon are the most important conducting material which we are using in our solid state devices. And yeah, silicon is most preferable in the nowadays in the industry, semiconductor industry. Entirely they are depending upon silicon only. So how the silicon is made and how the wafers are made, how the chips, what are the chipset we are seeing in our naked eye, how inside it, how the silicons are performing. Those things are the main thing where we are concentrating in this background semiconductor industry. So yeah, semiconductor, I think I don't want to go much beyond in depth with the semiconductor. So earlier silicon is intrinsic semiconductor, which I say. So when we are doping with any arsenic or phosphorus, then it will come as an extrinsic semiconductor, where we are using that semiconductor as an actual devices. So next time, just moving to next slide. So here's the silicon crystal, so which I already said. So usually silicon will be like this in this format. So this is the atomic structure of the silicon. So we need to break this valence bond so that silicon yeah. Then coming to the ASIC design flow. So ASIC is like application specific integrated circuit, as I said earlier. This is the you see here system specification. So it's like so for example, so for explaining this, I'm just taking a mobile, okay, any smartphone. So for a smartphone, we need to know how to make a smartphone. I want a smartphone with what and all things. How much camera I need, how much sensors I need, how much microphones I need, and what is the battery space I need. So those are the specification first we need to design. So that is the system specification. So in order to control all these, we have separate GPS and those things. So we need to control this. In order to control this thing, we need to know what and all the control element we need in a chipset. So that is a system specification. So the guy is like, for example, it's OnePlus or Vivo, whoever the company, that base level guy, first top level guy, they will come and say, these are the things I want in next release. Then the architectural design is a separate team is there. So they will architect based on the previous CPU and based on the previous core, they will try to upgrade the core. So they are giving the designs, and then those designs are converted into a functional design and logics, like actual gates. If you see, that's a gates base. Everything is a transistor. It's a basic thing. So those everything is made of gates. So they will convert that logic to a gate level design. So those gate level design is made to circuit level design. Then that is a physical design. That is finally coming to a physical design. That's where we are working here. So physical design here, I'm just showing you different steps of physical design engineering. So how the chips are finally processed here with respect to this. If you see here, so this is just like a software module. Up to this is just like a software. We are testing a software. Based on the software testing, then we are going to implement to the hardware. So that is the thing. So physical, from the physical design completely on a hardware testing, final chip processing, and final chip is made. So packaging and testing and fabrication. So finally we are getting a chip. So next we will move on to next how this physical design engineering actually we are working. So this is the physical design engineering. So I definitely need to thank Infochips, is the biggest semiconductor service-based company where earlier I have worked in this company also. So they are just giving a brief description of how physical design engineers are working here. So these are the steps we have to follow for delivering a perfect chip, for delivering a perfect SoC. We can say SoC means silicon on chip. So that is one kind of model. So we are used to give it to a chip. So as I already said, chip specification in the chip, what all I need and how the chip should be performed. From the chip, we have to using a software. We have RTL synthesis, we have Verilog code. There's a hardware description languages. In the later slide, I am just trying to explain those things. So there we have RTL synthesis. They are using the software. They are compiling and they are simulating those functional verification. Those will do. So once those things are perfect, for example, I am doing a calculator for arithmetic calculation. Those things. I need to design a calculator. So calculator, what all it need? It need to perform addition, subtraction, everything. So what are the calculations? Tan, cosecant, whichever thing it has to be calculated. So those. Then I said like power. So power also, right? For a 5-volt power we are using. So how much power and how much watt it is getting used for the chip, that is input, right? Beside how much battery we are using, but how much power we are consuming for that also different, right? If 500 mAh battery if you are using for our phone, and we have to know that at least that should stand for with respect to the normal calling or surfing and internet. So when you do research, you know how much it is getting drained, how much it is set, behavior of what we need. So they will check in the design entry level. So RTL synthesis is the function, it's registered transistor level. So they are converting what are the functions, that is to a transistor level they will convert. So based on that, they will. This is further as a software only. This is a hardware description language. They are using the hardware description language uh, to create an RTL, different RTL level netlist to us. So we will get that netlist and we will we'll convert that into a final product of chip. So netlist in the sense what I can say, a compiled program, a group of program which holding the behavior. Like for example, I have a program for GPS. So I have program for GPS as in inside the netlist. When I compile the netlist, it will give you a location. It will give a location of that as an output. So that is the first software compilation. First we will check in the software. Then only we'll going to implement is a GPS as a separate chip. That is hardware chips. So those functions, these guys are giving a check the RTL level. So whoever have first imagination, so imagination come into a design level. So that imagination we are making as an proper RTL mode. Then going back to next one, then chip partitioning means it is like we have for example, just consider a square. Okay, so we are dividing a square into 16 pieces. So like the square. So those 16 pieces, not only one person will go into work on a complete square. It's like if you take one chip, a square chip, each and every those were partitioned. That is further fit into multiple, like 4 times or 6 times. So we will take, each person will take only one block and they are going to perform that. Finally, those all the blocks are combined and they are keeping in the one simple chip. So that is what first we need to partition, and we have to give it to the respected teams. Go and you work on your own. You work on your own. And after that, we are combining all the chips and we will keeping in the one chip. That is the final chip. We are getting what we are seeing: i3 and i5, i7 Intel core chips and all those things and all. So definitely there is a design for testing will be there. That even we the built-in self-test is one of the things which we are keeping inside the chip itself, where chip creates an automatic pattern for input and it will automatically check itself. That means am I okay? Like it's a self-test. It will create an input. Based on the input, it will automatically check the output whether output is correct or not. Like that. If it is not, then it will give us a glitch and it will say here it is not okay. Then we will go and see further what happened there. So floor planning is like a blueprint. So if I say floor plan, it's like exactly how we are building a home. For example, 1,200 square feet. If you have a place, we have to build a home. So first, what we will do? We will go with the boundary. So once the boundary is free, then we'll go inside. So foundation will be there. That is different. The foundation is like a fabrication. I will say later. So it's like how we are dividing a home. So bedroom is there, the kitchen is there. So it's like how hall is there, how much. So those things are floor planning. Similarly, even in the chip also, we are floor planning it. How, where the inside, so inside the chip, there's number of transistors. So gather of transistor we call as IPs. It's intellectual properties. Those IPs where I need to keep. So I will show a diagram. So you will please understand what I'm trying to say here in the floor planning. So a good floor plan should come with what it should be. Chip size area should be small. So as I already said, each and every day, year by year, the chip size is coming small. So the routing should be clear. So routing means inside the chips there are a number of wire connections are going. We can't even see in our naked eye. It's a nanometer, 10 power minus 12. So we can't see such things. Sorry, 10 power minus 9. That much small is there. You can't see through your naked eye. It's all completely automation process. So those routings are there. So signal delays, those things were important. The signal delays is nothing but the timing. How much time, whatever function if I doing, those things has to become very fast. So move on to the next slide. So similarly, I don't want to go through much on these things. These are the steps. The placement is like where we need to place the particular cells. We used to call it as cells. How in human body we are having a building block is the cells. Like here also, a chip is constituted a single cell, a group of cell constituted chip. So where we need to place the standard cells like AND gate, OR gate, combination of multiplexes. Those are not there in the chip. So we need to identify where we need to keep all those things. So CTS, here we used to say clock tree synthesis. this is the tech what we are nowadays. You are seeing 2.3 gigahertz and 3 gigahertz and 1.8 gigahertz score like that. We are speaking about the mobile, right? It's completely depend upon this clock tree synthesis. How the clock is made, how the clocking is perfectly planned inside the chip is what is main thing. This clock tree is a major thing which decides the performance of chip, whether chip has to be good, fast or not, like that. So then routing, as I already said, routing is like wiring. So between the two gates, we need to wire the gate so that the signal will pass from one gate to another gate. So it's like how we are wiring the houses with the tube light. We have a switch here, and the tube light will be there, and we have a TV and everything. So how we are connecting from the switch to the TV, similar things we are doing a fab. We are doing that in a chip also. So that is what we are used to call as a routing. So routing is two types of routing is there: global routing and detailed routing. And I think I don't want to go much about this global routing and detailed routing. It's a vast theory. Routing itself, if we go then final. So I just want to this is the final verification. Then once I said I floor planned it, I CTS is synthesized, and my routing is complete, and the final chip, what I have to do, physical verification. Chip has to be tested whether the chip is properly working or not. That two wires should not be merged. It should not cause a short, right? So that those kind of some physical verifications are there. Those checking and all we are doing in a final verification. And last step is what? Graphical data stream information, GDS we used to call it as. So this GDS what we are giving as it is a software format. So this GDS has to be taken by the fabrication unit like Intel, Samsung and Apple. Those they have separate fabrication units. So they will take their own GDS format and they will give it to the fab. So once they handle to the fab will take care of everything and it will give a final finished chip product. So these are the physical design engineers what we are doing. It is a completely software program. So the program have a automated proc. So those procs are definitely made from the Perl scripting. So I think maybe Java, C++ normally you are aware, but Perl is also a software tool, which programming tool, which we are using in semiconductor industry. And another language is the TCL. We call it the tool command language. In short form, we call it Tickle. So this Tickle language also we are using most of the EDA tools, electronic automation tool. So that means we need a tool to design, right? So just like that, we can't go on. Like if you want to go and write a Java, you need Eclipse software. So inside Eclipse software, you will write a Java command and you will execute it, and you will see the final product. So same thing, we are having another tool like IC Synapse, Cadence, and Mentor Graphics. Those were the vendors. They have tools. Where we Intel and Samsung like guys are hiring the tool. That means bought the tool for licensing. So each tool licensing will cost more $1 billion. So that's what. So that's the revenue how they are earning like Cadence and Synopsys. So using that tool only we can able to go and implement all these changes which I am saying. So next move on to next slide. So yeah. So here is a chip. So usually we will see a chip in the right side. I have put Intel Core i5. So if you open our PC or if you open our normal desktop computer inside CPU, you will see a chip like this on the right side. But actually how the chip will be inside. So here is what we are doing. How we are floor planning. This is a complete SoC we used to call as a silicon on chip. So as I already said, floor planning. So this is a SoC floor planning. See, this is a boundary. So these boundaries are having with the pads. We will call this as IO pad and power pads. So from here only your input will be processed here. It's like a CPU. So from these IO pads only input will be get interchanged. Input and output will be interchanged through this. It's like a gateway. So this is a boundary also. I can say it like a boundary. As I said, for a home we need a boundary, right? So this is the boundary. So further, if I go here, as like how we are planning a home, same thing we are planning. So I am saying this SRAM should become this is a memory. So random access memory, nowadays even for buying a phone, we used to say how much RAM. Those are dedicated RAM. Here, this RAM is not a dedicated RAM. It is a part of a chip. But nowadays, what we are using in mobiles and what we are using in laptops, those were the dedicated RAMs. You have 8 GB RAM, 12 GB RAM, 16 GB RAM. So those things are nothing but those are random access memories. So based on how much high the RAM, how that much the fast your device will be. So that's what we used to. So those things. So this is the RISC structure they are using in this Raven IP. It is a Raven SoC. So this is a RISC-V microprocessor. So how they are? So why I'm showing this? This is how inside this chip how it will be. So we are seeing this chip, but actual inside how it will be. We have a PLL. So this is the clocking structure. I said right, clock. So 8 cross PLL. That means it will give 8 different types of clock signal. For example, you have 3 GHz, 4 GHz, and now we are at most nearing to 3 GHz in iPhone 11 and some other advanced phones also. We are having a 3 GHz. So everything will come from here. So he is the main person, and he clocks the entire unit. So that only making it to work. Not only a clock also needed, definitely power also needed, because we need a power also. So usually power pad will be at the edge. They will keep these power pad at the edge to give a power to these all circuits. Definitely to run, as I already said, semiconductor, we need a external potential to run. So external power should need to run all these things. So that's what we have 12-volt power across the SoC, so that it will get it work. So I'm just giving you a glimpse here how it will be like this. This is a semiconductor, one of the SoC. So where we will work, either as a person we will work on entire, or we will at a block level. This small block is assigned to one person, they have to work. This small block has to be assigned. This is a partitioning. They're partitioning the block and give it to a separate block. This will be, some team will be handling this, some team will be, these are sub-FC they used to call. So further, this sub-FC, if you see this pink color, this alone is given to some other team. That alone will be processed by 2 or 4 engineers. So see, for this complete chip, how much man work you need if you, for this R&D, how much man work if you need. There will be thousands of men for this complete chip, not a single man. So that's what they are. So for R&D itself, they are investing billions of dollars. So that once R&D is successful, they'll give to a product. They are marketing it, right? So that's what they're investing thousands of billions of dollars here. Yeah. Then I move to a next thing. So I hope you may understand. You guys understand the basic of how the internal chip will be there. Yeah. Then as I already said, there is a language, hardware description language. This is an tool identify language. It is facilitated a complete language, and it is used to describe the structure and behavior of the electronic circuit. If I given an example in the next slide. So what is the electronic circuit? For example, if you take one multiplex, the use of mux. So mux is so first basically we will see, for example, a mux have one input, many output, or many input or one output, or one input or many output, like that it will be there. Where the mux will be used is, now itself I say that the transmission and receiving end will be there. We have a transmitter on one end, receiver at one end. So we usually use the mux as the transmitter and demux as a receiver. Mux, it will transmit entire, for example, for one phone to another phone. I want to transmit a image. Earlier it was like IR red and infrared are used to transmit, right? There is a mux will be there, either and demux will be there. If I send a message to a nearby phone using a WhatsApp or whatever the thing, it will decode. So the decode, how it will happen, all through a mux. It will decode it, and it will send to the normal radiation, electromagnetic radiation. From that, as a packet, it will receive at another end. So these electronics electrical, it's a vast sea. So just I give a glimpse how a mux is working. So what are the 3 common languages we used to say as Verilog, VHDL, and System C. So still now we never worked on System C. It is the newest one where we are eager to work on it, System C. But as a physical engineer, I don't get a chance to work on these languages because these languages are as a front end. We used to say as a front end and the back end. So we are working in back end. So these language one person will work in the front end. As I already said, these were RTLs. They were RTL coders. They will create a behavior simulation. So what we imagine a chip as a physical chip, those things they will have in the software format. Those software will be completely handled by the front end people. So those people will called even as RTLers. Then moving to the next slide, I am just giving example for only one language. This is VHDL, Verilog Hardware Description Language. It is as I already said, there is a MUX. So what is the purpose of MUX? We have it's like a decision making. We have 4 inputs, but not all inputs will go as one input. Either only one input we want to get output. So which is a priority? This priority will be selected by a select tool. So which is a priority one? I am getting a call. I am seeing a video here. I am telecast. I am taking an image, or I'm recording image here. I am also hearing a song and those things is there. So immediately at the time one call is coming. This call is coming at the I3. So here it will take a decision. So call is the most preference than any other thing, right? So that's the base for the cell phone what we are using. So now it will allow only I3 as one area. So why will be an I3? Because I3 is the most prioritized as a call. So that multiplexer will decide this. So here's the description language how we are using in on a semiconductor industry at the front end. So here they will say as a module. Everything we will consider as a module. So how it's a name you can give as a name MUX. How this is the name we will give on our own too. So 4+1 MUX is here is 4 input and 1 output. That's what we are calling it 4+1. So here we have, so inputs are here. We are declaring the inputs and outputs. So here input declarations happened. So after declaring, we need to say which is an input, which is an output. So we are declaring these were input and bit. This is array. Okay. So since these were 4 inputs are there in array format, so we are declaring as an array, and those are select signal also we are having. So select will be either 1 or 0. So that's what is 1 is to 0, and output is Y, and yeah, register is Y. Temporarily that Y is getting registered to some other flip flops. Those registered. That's what we are giving as a register Y. So these are the behavior simulation. Even we have structural description also is there, and programmer description also there. So here it is the behavioral description where it will select. So which one I need to select, I0, I1, I2 or I3 based on case select. Based on the case select, I will select this thing. So it's like how we are using case statement in C and C++. Similarly here also similar thing. Concepts are same, but the way of approaching a VHDL is different here. So as I already said, multiplexer and demultiplexers are work together to carry out the process of transmission and reception. So receiving and transmission is a major thing for any communication. For EC, if you say, so transmission and receiving is a major thing, right? Yeah. So that's what MUX is performed here. So then, as I already said, there is a software language which we are trying to use. Here is Perl and Tickle programming. So we are using a Perl here. Why we are using a Perl here? So what automation tools we are using? As I already said, EDA tool, Synapses and Cadence, those tools are already automated. We don't need to go for placing. So we are having, for example, gates I mentioned. We are having millions of gates are there. So a person like a human being, they can't go and place millions of gates separately alone. Okay, so they will give it to the script. They will know. So it will collect all these types of cells, and it will say, so place in one area. How it will place the area? We will give the script based on timing approach. This guy, one guy speak to another guy. So we need to keep that guy close. So that everything will be automated. It's like a AI, artificial intelligence. It has to be we will scripting like that. So if the person is if this gate is talking to this gate, and we need to keep it near to the gate and through a wire like that. If you are saying as a script, the script will perform and the tool will perform. So every tool as a EDA tool, they will obey the Perl scripting and Tickle scripting, And now most of the semiconductor industries, they are using tickle scripting, and Perl also an upcoming thing, and we people are learning a Perl to write our own scripting, because we need to analyze the reports, right? So reports having thousands and lakhs of lines will be there, right? Lakhs of reports will be there. So I can't go and read each and every line in the report. So we know which for this particular report which is needed summary. So where the summary will be there, we need to write a script, and we will ask the tool dump the summary alone. I need to see the summary. Like that, we need to scripting. So for that, we are using tickle and Perl. So it is a just a glimpse. I'm just saying how the tickle will be there. So it is just a comparison. So set A 10, and we are setting a value 10 to a variable A. Again, we are setting B. We are setting whatever it will be, whatever the output will be, that output will go to the B. So what we are doing directly, we are expr is an expression. Directly we are saying $A means the content of the A. So content of A, whether it is equal to 1. So now it is saying 10 is equal to 1 or not. If it so, yes or no. It's like, so if content of A is equal to 1 is not, because A is 10. No. So it will choose the 30. Okay. So we say puts the value of B. So again we are saying B, whether that content of A is equal to 10. Yes. So when it is a 10, it will select this 20. So usually, so when we compile this thing, we will know the output of the B will be like this way. So this is just a basic tickle scripting. I'm just saying how tickle scripting are using here. So similarly, we are saying here, instead of A is equal to 10, we will say, we will grep the cell name. So take all the combined cell names. In the set B, we will say put if this cell is talking to B, we will put in some other cell. Now we will say if A and B is talking, means put A and B together. Like that, we will write a proc. We will source the proc to the idiot tool. It will do it process. Then we will see in the final output. So okay, I think that physical design engineering completely we have. I think you have better glimpse how chip is there. So here that's just a comparison. It's a basic knowledge. So now we have latest Apple A3 Bionic chipset, and which was used in iPhone 11 and all. So how Apple are investing? So here I am seeing, right, how they are investing for R&D. See, these are separate teams. We have validation team, prototype, software team is there, physical design, what we are doing, verification team, architecture and IP qualification. So this is for the 5 nanometer. So I will say what is the technology later. So this is a 5 nanometer chip. So how much they are investing here? You see, there's a dollar, $542 million. $1 million they are investing for R&D itself. This is Apple. So I just want to say this 60 nanometer, 10 nanometer are now, so it is already become an older technology. So now we are surveying in 10 nanometer. Now if you see Snapdragon 865 processor having a 7 nanometer tech, and 875 it will going to come. They are in that they are using 5 nanometer tech. So why they are saying nanometer, those things I will just say. So it's just a comparison, right? So 60 nanometer means how much transistor will be there. It is billion unit, you can say 3.3 billion transistor will be there. But in 3 nanometer, they are using how much? 14 billion transistors are there. So the number of transistor increases, but sizes of chip area is reducing. See the chip area, 122 micron to, now it is just reduced to 85 micron. So this is the technology. So chip size is reducing, but internal transistor size is increasing. That is the major challenge in the semiconductor industry. Okay, I'm just further moving to. So I said, right, 10 nanometer, 7 nanometer. What is this nanometer? Why we are saying as nanometer? It is not just chip size. It's the gate size. How a gate we are using. This is the gate size. Based on the gate length, we will say the nanometer. So here technology mean the technology of the chip made or fabricated with respect to size or length of the gate. So here is the CMOS structure. It is a complementary matlab se semiconductor transistor. So transistor structure will be, so this length, based on this length only. Nowadays we are going to call a chip is 7 nanometer chipset, 5 nanometer chipset, like that, because of this only. So it is a basic knowledge we need to know. As a 7 nanometer chip, we are buying any phone, mobile phone. They are saying microprocessor and Snapdragon 5 nanometer chip means we need to know what is nanometer. It is not like chip is that much size. It is that inside the transistor using in the chip is nanometer. That's 5 nanometer. So this is the most advanced FET. It's going to come for 3 nanometer technology. So this planar FET is used in 28 and earlier technology. This is for FinFET, they are using 10 nanometer, and GIF FET they are using in 5 nanometer, and finally the nanosheet they are going to use in the 3 nanometer. Already the R&D is going on in both Intel, everyone is going through it. So next Intel, Intel has one law. So that's the Moore's law they used to say. Moore's law, that means for every 24 months or for every 2 years, the number of transistors in the chip should be doubled. So as I already said, transistors should be doubled, but size of the gate should be. So here if you see transistor is doubled. So that is his technology. So from 3.32 I have to go with 4.3 billion. Then I have to go with 6.9. Then 10. So transistor is doubled, but see size of the chip area will be reduced. This is what the Moore's law. So he's one of the Intel co-founder. And yeah, also I just for you guys, I am just give a small introduction about the video how a chip is getting fabricated. Yeah, let's have a look on. These are the plates. This they are calling as wrapper. So now UV processes are going on. So these are the list of process they are going in the fabrication. So if you watch here, there will be millions of transistors there. This is etching. This is now chemical UV is they are fixing. They are giving a chemical properties to the semiconductor. Now this is a gate, a single gate. How a single gate is fabricated or processed here, it is showing here. This is the gate, insulating material. Okay, so basically it's like an insulator. So the gate will be insulated here. So they are giving a layers, metal layers of processing here. Charging it. So once we charge the single transistor, we will connect all the transistors together. See here the transistors are getting connected. This is what I call as routing. So this is where these are the wires which we are routing. Wafer from one wafer getting the chip. Now the chip one keeping the chip. So this is how the chip is delivered to us. Now we are testing the chip. The chip is functionally working or not. That's it. We are packaging the chip. Similar thing. So how the fabrication unit is working here is also another video is for you guys. So we will watch it.
The world is producing data at an unprecedented rate, faster than our ability to analyze and understand it. To move, store, and compute all of this data requires incredible processing power. From the blazing speeds of our devices to blazing trails within AI, Intel builds chips that are at the heart of nearly everything. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology. This strong silicon foundation is what gives each Intel chip limitless potential. At the heart of all modern electronics, the transistor is a tiny switch, 10,000 times smaller than a human hair, that controls the flow of electrons through a circuit. To build a processor, billions of transistors are packed into an area no larger than a fingernail. It's one of mankind's most complex feats, called FinFETs. FinFET construction requires first building a channel in the form of a fin. Intel has devised several innovations to overcome fundamental barriers to continued transistor scaling. One such innovation is a breakthrough fabrication method called gate last. It involves building, then removing a temporary gate in order to precisely place the dielectric material and metal gate. This allows for the gate to wrap around the fin and control the flow of electrons through the channel. Another invention moves the transistor contact directly over the active gate. To accomplish this, the gate material is recessed and then filled with insulating dielectric material to prevent the creation of a short circuit. Next, the dielectric near the gate is etched, filled with metal, recessed, and capped to allow a novel self-aligning process that enables the high-density contact geometries. Now, the dielectrics are etched selectively to expose only the desired part to connect to the first metal lines. This is done through an innovative via etch and deposition scheme, allowing contact over active gate to happen. Finally, dozens of layers of metal interconnect lines are added to complete the circuit. After more than 1,000 of these complex steps, the wafers are finally prepared for singulation and packaging. Innovative processor packaging has become a critical feature of advanced computing architecture. 2D and 3D packaging technologies are enabling new device form factors and additional boosts in performance and energy efficiency. Testing of the final product ensures that every chip exceeds our performance and quality standards. In addition to adding more performance and features with each new processor generation, Intel's integrated design and manufacturing capabilities have enabled humanity to innovate game-changing technologies that impact nearly every facet of modern life. Intel keeps powering the world. At the same time, we're powered by you, the makers, the dreamers, the doers, the people who share in our history of making the world smarter, faster, and more connected.
So hope you are seeing the complete fabrication unit, how Intel is working in the fab unit. So those were the webs, how the chipset, once what we are giving a GDS2 earlier I said in that chipset. So that GDS2 is given to this fab unit. So from that our output, this fab unit take as an input and it will do the process which we see in the earlier video. Then what are why are we are doing all this stuff? All this because of this IoT, the concept, it's the Internet of Things. So next thing is what we are controlling everything through the mobile phone. If you have a smartphone, I can control the light, I can control that TV, I can control. So now we are having a air blaster earlier. So even if you have air blaster, we are controlling AC, TVs and those things. So from that is IoT is more advanced. So IR blaster is directly using the IR direct to direct contact of the metal of the two devices. But now IoT is not like that. It is internet. For example, I have an IP cam. We are having IP cam and camera is there. We are connecting to the internet. So anywhere in the world, if I go there, I will see those whichever it is recording. I can see anywhere in the world. So those things are the concept of IoT. So anywhere in the world, I can control my home. So that is what a smart home, that is what each and every industrialist are working hard to get the smart home as a future technology, as a future home to every people. So that is what each and every day these IoTs are getting developing. It's a so why I'm saying a developing tech is, it is not completely developed. So that's what I'm saying. And there's a developing tech. So I'm just giving a IoT basic concept how.
The Internet of Things, or IoT, is influencing our lifestyle from the way we react to the way we behave. From air conditioners that you can control with your smartphone to smart cars providing the shortest route, or your smartwatch which is tracking your daily activities. IoT is a giant network of connected devices. These devices gather and share data about how they are used and the environment in which they are operated. It's all done using sensors. Sensors are embedded in every physical device. It can be your mobile phone, electrical appliances, vehicles, barcode sensors, traffic lights, and almost everything that you come across in day-to-day life. These sensors continuously emit data about the working state of the devices. But the important question is, how do they share this huge amount of data and how do we put this data to our benefit? IoT provides a common platform for all these devices to dump their data and a common language for all the devices to communicate with each other. Data is emitted from various sensors and sent to IoT platforms securely. IoT platform integrates the collected data from various sources. Further analytics is performed on the data and valuable information is extracted as per requirement. Finally, the result is shared with other devices for better user experience, automation, and improving efficiency. Let us look at a scenario where IoT is doing wonders. In an AC manufacturing industry, both the manufacturing machine and the belt have sensors attached. They continuously send data regarding the machine health and the production specifics to the manufacturer to identify issues beforehand. A barcode is attached to each product before leaving the belt. It contains the product code, manufacturer details, special instructions, etc. The manufacturer uses this data to identify where the product was distributed and track the retailer's inventory. Hence, the manufacturer can make the product running out of stock available. Next, these products are packed and parceled to different retailers. Each retailer has a barcode reader to track the products coming from different manufacturers, manage inventory, check special instructions, and many more. The compressor of air conditioner has an embedded sensor that emits data regarding its health and temperature. This data is analyzed continuously, allowing the customer care to contact you for the repair work in time. This is just one of the million scenarios. We have smart appliances, smart cars, smart homes, smart cities, where IoT is redefining our lifestyle and transforming the way we interact with technologies. The future of IoT industry is huge. Business Insider Intelligence estimates that 24 billion IoT devices will be installed by 2020, and IDC predicts that IoT revenue will reach around 357 billion in 2019, resulting in a lot of job opportunities in the IT industry. Want to become a part of the IoT revolution? Come and master IoT with AJKCAS.
So what we have seen earlier is an IoT concept. So this is what. So how we are controlling, how from the silicon, from the chip, now we are controlling a device through another device. That is what the IoT concept is there. So here, that's what I'm saying. We have a smart oven is one of the concepts which we are using in IoT. So this is the future thing, where this is the oven. So it has the preset settings and heat settings, everything will be there. So these are completely an AI control. So how it will be there? So we have touch sensors nowadays. So similar thing. So maybe you can observe through the video. So one touch will open. Just touch it and it will close and it will open. This everything we will monitor to the mobile. So that is the main concept of IoT. That is the way we are speaking as a smart home or smart things. So this is the other further advanced concept of this is a kind of smart bangle. So like a smartwatch we use to say a smart bangle. concept of smart bangle. So I'm coming to the final presentation where how a smart home will be. So this is the final video. You can watch it. How a smart home will be. So this will be a smart home technology. It's a concept-based smart home concept. Everything is wireless. All internet of control, wireless. Smart bulb and control. That's the immediate reaction. That's the feedback. So the feedback of anything is very fast move and highest response. Nowadays we got all the small companies. So finally I come to conclusion of my Silicon to Smart Home session.
Thank you, sir, for your amazing effort and keynote presentation.
Thank you, everyone.
Once again, thank you all for being a part of the event. Thank you.